Hello and welcome to Science After Dark. Before we begin, take a moment to like the video, subscribe to the channel, and let me know in the comments where you're watching or listening from tonight. Because wherever you are, whether it's a quiet room, a late night commute, or somewhere under a sky full of stars, you're surrounded by the same tiny building blocks that shape the entire universe. Take a slow breath. Right now, everything around you, the air, the walls, your body, even the device you're listening on, is made from atoms. Incredibly small, impossibly numerous, and quietly working together to create everything you can see, touch, and experience. And yet, atoms themselves are almost entirely empty space. Tonight we're going to drift into that hidden world, not in a rushed or technical way, but slowly, gently, as if we're zooming out and in at the same time. From the smallest particles that flicker into existence to the vast structures of stars and galaxies, all connected through the same simple ingredients. Because one of the most fascinating truths in science is also one of the most calming. Everything is made of the same few things, arranged in different ways. The calcium in your bones was forged inside ancient stars. The oxygen you breathe has travelled across cosmic distances. The carbon in your body, once part of a star that lived and died billions of years ago, has become part of you, here, now. And all of it begins with atoms. In this journey we'll explore what atoms really are, not just as textbook diagrams, but as living, dynamic systems. We'll move through their hidden structure, their strange quantum behaviour, the forces that bind them together, and the quiet rules that allow them to form everything from water and stone, to planets, to life itself. We'll see how stars act as cosmic furnaces, how explosions scatter the ingredients of worlds, and how, over time, those same atoms come together again, forming something as complex and fleeting as a human thought. There's no need to rush, no need to hold on to every detail. Just let the ideas settle, like dust drifting through space. Because in the end, this isn't just a story about atoms, it's a story about connection, about simplicity giving rise to complexity, and about how, in a universe that can feel unimaginably vast, everything is quietly made from the same shared foundation. So, as you settle in, wherever you are, let's begin at the smallest scale imaginable and discover how atoms build everything. If you take a moment to look around, really look, it can begin to feel almost overwhelming. There is so much variety, different shapes, textures, colours, temperatures, from something as soft as a breath of air to something as solid as stone. And yet, beneath all of that variety, there is a remarkably simple idea quietly holding everything together. All matter, everything you can see, touch, or even imagine physically, is built from atoms. It does not matter whether you're looking at a distant star, a drop of water, a grain of sand, or your own hand resting gently beside you. At the deepest level, they are all made from the same kind of building blocks. Not similar building blocks, the same ones. It is a little like discovering that every book ever written, every poem, every story, every idea, is composed from the same small alphabet. The differences come not from the letters themselves, but from how they are arranged. Atoms are those letters, and what is quietly astonishing is that this idea, that everything is made from tiny, indivisible units, is not new. It stretches back more than 2,000 years, to a time when there were no microscopes, no particle accelerators, no laboratories filled with precision instruments, only thought, careful observation, and imagination. In ancient Greece, a philosopher named Democritus proposed that if you kept cutting a piece of matter into smaller and smaller parts, eventually you would reach something that could not be divided any further. He called these smallest pieces atomos, meaning indivisible. It was a bold idea, especially in a world where most people believed matter was continuous, endlessly divisible like water flowing into smaller streams. Democritus suggested instead that reality was granular, made of tiny discrete units moving through empty space. His student, or perhaps more accurately his intellectual successor, Epicurus, expanded on this view, imagining atoms moving, colliding, and occasionally swerving in unpredictable ways. That small addition, the idea that motion was not perfectly fixed, hinted at a kind of early randomness, a whisper of uncertainty long before modern physics would give it a formal name. Later, the Roman poet Lucretius carried these ideas further in his work De Rerum Natura, or On the Nature of Things. He described atoms falling through the void, combining to form everything from rocks to living beings. His writing was not just scientific speculation, it was poetic, almost meditative, an attempt to explain the world in a way that felt both logical and deeply human. And far from Greece, in ancient India, another thinker named Canada developed the Vaisheshika school of philosophy. He also proposed that the world was composed of indivisible particles, which he called anu. These particles combined in different ways to form the substances we experience. What is striking is that these ideas emerged independently, in different cultures, separated by vast distances. There was no shared laboratory, no common data set, just a shared curiosity about what reality is made of. Of course, these early atomistic ideas were philosophical rather than experimental. There was no way, at the time, to test whether atoms truly existed. For many centuries, the idea faded in and out of favour, often overshadowed by other explanations of matter, and yet it never fully disappeared. Much later, in the early 1800s, a scientist named John Dalton revisited the concept, this time grounding it in careful measurements. He observed that chemical elements combine in fixed ratios. For example, that water is always made from 2 parts hydrogen and 1 part oxygen. From this, he concluded that matter must be composed of discrete units that combine in specific ways. Dalton's work transformed atoms from philosophical speculation into a scientific theory. Still, even then, atoms remained invisible. They were inferred, deduced, but not directly observed. There were scientists like Ernst Mach who remained skeptical, arguing that atoms were convenient ideas rather than real entities. It was not until the early 20th century that this changed. A physicist named Jean Perrin studied the motion of tiny particles suspended in liquid, a phenomenon known as Brownian motion. First observed by Robert Brown, this jittery, unpredictable movement was eventually explained by Albert Einstein as the result of countless collisions with invisible molecules. Perrin's careful experiments measured this motion in detail, providing strong evidence that atoms and molecules were not just theoretical constructs. They were real, physical things. And from that point on, the idea of atoms became firmly rooted in science. But even now, when we say that everything is made of atoms, it is important to understand that atoms are not little solid balls, like tiny marbles or grains of sand. That image, while simple, is misleading. Atoms are dynamic. They are systems, patterns of energy and interaction. Most of an atom is empty space, with a dense nucleus at the centre and electrons existing in regions of probability rather than fixed paths. So when we say that the world is made of atoms, we are not saying it is made of tiny solid objects stacked together like bricks. We are saying that reality is built from structured patterns, from relationships between particles, from interactions governed by underlying laws. In that sense, atoms are not just physical building blocks, they are also conceptual tools, ways of understanding how complexity emerges from simplicity. From just a handful of fundamental particles, arranged in different ways, arise all the substances we know, the softness of fabric, the strength of steel, the transparency of glass, the warmth of skin. All of it, variations on a theme. And there is something quietly comforting in that, because it means that beneath all the apparent differences in the world, there is a deep unity, a shared structure, a common origin. The same types of atoms that make up distant stars are present in the air you breathe. The same physical laws that govern galaxies also shape the smallest chemical reactions in your body. It is easy, in daily life, to experience the world as fragmented, separate pieces, disconnected events. But at the atomic level, everything is part of the same continuous story. A story that begins not with complexity, but with simplicity. A few fundamental components, interacting over time, gradually building up into the vast, intricate universe we find ourselves in. And as we begin to look more closely, to gently explore what atoms really are and how they behave, that simple idea will unfold into something far richer, far stranger, and far more beautiful than it first appears. If everything around you is built from atoms, then it becomes quietly important to ask a simple question. What exactly is an atom? Not the simplified image from a textbook, not the tiny dot in a diagram, but the real thing, the physical entity that underlies every material in the universe. In modern science, an atom is defined as the smallest unit of a chemical element that still retains the properties of that element. That definition carries a lot of meaning. It tells us that if you take a piece of gold and divide it again and again, eventually you reach a single gold atom. And that atom will still behave like gold. It will still have the same identity, the same fundamental characteristics. But if you go any smaller than that, if you break that atom apart, you no longer have gold, you have something else entirely. This idea that there is a smallest meaningful unit for each element was formalized in the early 1800s by John Dalton. Dalton was not working with powerful instruments or advanced imaging. Instead, he relied on careful measurement and observation. He noticed that when elements combine to form compounds, they do so in fixed and predictable ratios. Water, for example, is always composed of hydrogen and oxygen in a specific proportion. No matter where you find it, no matter how it forms, that ratio remains constant. Dalton proposed that this consistency could only be explained if matter were made of discrete, indivisible units, atoms, that combine in simple numerical relationships. It was a beautifully straightforward idea, and like many powerful ideas in science, it explained a wide range of observations with a single underlying principle. But there was still a problem. No one had ever seen an atom. For many scientists, this raised an uncomfortable question. Were atoms real physical objects, or were they simply useful concepts, convenient tools for explaining chemical behavior? One of the most prominent skeptics was Ernst Mach, a physicist and philosopher who argued that science should only deal with directly observable phenomena. Since atoms could not be seen, touched, or measured directly at the time, Mach was hesitant to accept them as real. From his perspective, atoms were more like mathematical shortcuts than physical entities, and for a while, that skepticism was taken seriously. Science, after all, thrives on questioning its own assumptions. The turning point came in the early 1900s, through a phenomenon that, at first glance, seemed almost trivial. If you place very small particles, such as pollen grains, in water and observe them under a microscope, you will notice that they move in a jittery, erratic way. They do not drift smoothly. Instead, they twitch and dance, constantly changing direction. This motion, first carefully described by the botanist Robert Brown, became known as Brownian motion. For a long time, no one could fully explain why it happened. Then, in 1905, Albert Einstein proposed a solution. He suggested that the motion was caused by countless collisions between the visible particles and much smaller, invisible molecules in the liquid. These molecules were moving constantly, driven by thermal energy, and their impacts pushed the larger particles around in unpredictable ways. It was a bold explanation, because it relied on the existence of atoms and molecules, things that had not yet been directly observed. To test this idea, a French physicist named Jean Perrin conducted a series of meticulous experiments. He measured the motion of particles suspended in liquid and compared the results to Einstein's predictions. The agreement was striking. Perrin was able to calculate quantities such as Avogadro's number, which tells us how many atoms are present in a given amount of substance. His results matched theoretical expectations so closely that it became very difficult to argue that atoms were merely abstract concepts. They were behaving exactly as real, physical entities should. Gradually, the scientific community shifted. Skepticism gave way to acceptance. Atoms were no longer just a useful idea. They were part of the physical world, and yet, even as atoms became accepted, our understanding of what they actually are began to change. It is tempting to imagine atoms as tiny, solid spheres, like miniature billiard balls. That image is simple, and for certain purposes it can be helpful, but it is not accurate. An atom is not a solid object in the way a stone or a piece of metal is solid. It is better understood as a dynamic system, a structured arrangement of smaller components interacting through forces. At its center is a dense region known as the nucleus, which contains protons and neutrons. Surrounding this nucleus is a region occupied by electrons, but these electrons do not orbit the nucleus in neat circular paths like planets around a star. Instead, they exist in what physicists call probability distributions. regions where the electron is likely to be found, but never pinned down to a single precise location. This is one of the key insights of quantum mechanics. At the atomic scale, certainty gives way to probability. Instead of saying exactly where an electron is, we describe where it might be and with what likelihood. So an atom is not a tiny solar system. It is more like a cloud of possibilities, shaped by underlying physical laws. And then there is the matter of space. If you could somehow enlarge an atom to the size of a large stadium, the nucleus would be about the size of a small marble at the center. The electrons would occupy a vast region around it, and most of that space would be empty. Not empty in the sense of nothingness, but empty in the sense that there is no solid material there. This means that what we perceive as solid objects, a table, a wall, your own hand, are, at the atomic level, mostly empty space, structured and held together by forces. It is a slightly unsettling thought at first. If everything is mostly empty, why does it feel solid? The answer lies in the interactions between atoms. When you press your hand against a surface, the electrons in your atoms repel the electrons in the surface. This electromagnetic interaction prevents the atoms from passing through each other, creating the sensation of solidity. So solidity is not about matter being tightly packed like bricks. It is about forces, interactions, resistance. And this brings us to a deeper understanding of atoms. They are not just objects. They are systems of interaction, patterns of energy and force that maintain stability over time. Each atom is defined by the number of protons in its nucleus, which determines its identity as a chemical element. A hydrogen atom has 1 proton, a carbon atom has 6, an oxygen atom has 8. That number is not arbitrary. It is the defining feature that determines how the atom behaves, how it interacts with others, and what kinds of structures it can form. From these simple differences, just the number of protons, arises the entire diversity of the chemical world. It is a bit like having a small set of musical notes that can be arranged into an almost infinite variety of melodies. And so, atoms become the starting point for everything we observe. Every molecule, every material, every living organism, all begin with atoms combining, rearranging, and interacting in countless ways. They are the foundation upon which chemistry is built. And through chemistry, they become the foundation of biology, geology, and even much of physics. It is easy to overlook something so small. Atoms are far beyond the reach of our senses. We cannot see them directly, cannot feel them individually, cannot hold one in our hand. And yet they are everywhere. They are in the air that moves gently around you, in the surface beneath you, in the quiet rhythm of your breathing. Each second, trillions upon trillions of atoms are interacting, exchanging energy, forming and breaking connections, all of it happening silently, invisibly, and continuously. So when we ask what an atom is, the answer is not just a definition, it is an entry point. A way of beginning to understand how the vast complexity of the universe arises from something remarkably simple. A small, structured system, governed by consistent rules, capable of forming everything we know. When we first begin to understand atoms, it can feel like we have reached the smallest meaningful layer of reality, a kind of final boundary, a place where things simply stop. But nature, it turns out, is rarely so simple. As scientists continued to explore matter more closely, they discovered that atoms themselves are not indivisible. They are composed of smaller parts, each with its own properties, behaviors, and role within the structure. At the center of every atom lies the nucleus, a compact region containing protons and neutrons. These particles are far smaller than the atom itself, yet they contain nearly all of its mass. If the atom were expanded to the size of a cathedral, the nucleus would still be smaller than a grain of sand at the center, holding almost everything of substance. For a time, protons and neutrons were thought to be fundamental. They seemed stable, well-defined, and indivisible in any practical sense. But as experimental physics advanced, particularly in the mid-20th century, this assumption began to shift. Researchers started to probe matter at higher and higher energies, using particle accelerators to collide particles together and observe what emerged. Facilities like the Stanford Linear Accelerator Center in California became places where matter was not just observed, but carefully taken apart. What scientists found was unexpected. Protons and neutrons were not solid indivisible units, Instead, they behaved as though they contained smaller, point-like constituents. These internal components appear to carry fractions of electric charge and interacted in unusual ways. In 1964, two physicists working independently, Murray Gell-Mann and George Zweig, proposed a new model to explain these observations. They suggested that protons and neutrons are made of even smaller particles, which Gell-Mann named quarks. The name itself has a slightly playful origin, taken from a line in James Joyce's novel Finnegan's Wake, a rare moment where literature quietly meets particle physics. Quarks are not like the particles we encounter in everyday experience. They come in different types, known as flavors, with names such as up, down, charm, strange, top, and bottom. Despite the whimsical naming, these categories represent very real differences in mass and behavior. A proton, for example, is composed of 2 up quarks and 1 down quark. A neutron is made of 2 down quarks and 1 up quark. These combinations are not arbitrary. They are governed by precise rules that determine how quarks can combine and remain stable. One of the most unusual features of quarks is that they are never found alone. This phenomenon is known as confinement. No matter how much energy is used to try to separate them, quarks remain bound together, always appearing in groups. The reason for this lies in the force that holds them together, known as the strong nuclear force. This force is carried by particles called gluons. The name is quite literal. Gluons act as the glue that binds quarks together inside protons and neutrons. But unlike glue in the everyday sense, this force becomes stronger as quarks are pulled apart. It is a bit like trying to stretch a rubber band that becomes tighter and tighter the more you pull, until it eventually snaps. Not into 2 separate ends, but into new combinations that still contain quarks bound together. So even at this deeper level, matter resists being fully separated into isolated pieces. As these discoveries accumulated, physicists began to organize the growing list of fundamental particles into a coherent framework. This framework is known as the Standard Model of particle physics. The Standard Model describes all known fundamental particles and the forces through which they interact, with the exception of gravity. It is one of the most successful scientific theories ever developed, capable of making predictions that match experimental results with extraordinary precision. Within this model, matter is built from a small set of elementary particles. There are quarks, which combine to form protons and neutrons. There are leptons, which include electrons as well as less familiar particles like muons and neutrinos. And there are force-carrying particles, known as gauge bosons, which mediate the fundamental interactions. These include photons for the electromagnetic force, gluons for the strong force, and particles known as W and Z bosons for the weak nuclear force. Each of these particles has specific properties, mass, charge, spin, and each follows well-defined rules of interaction. What is remarkable is how few of them there are. All the visible matter in the universe, every atom, every molecule, every star and planet, is built primarily from just a handful of particles. Up quarks, down quarks, and electrons form the foundation of ordinary matter. From this small set, everything else emerges. It is a little like discovering that an entire language, with all its poetry and complexity, is written using only a few dozen characters. But there is an important shift in perspective here. Atoms, which once seemed like the fundamental building blocks of reality, are now understood as composite structures. They are built from smaller components, which themselves are governed by deeper laws, and even those deeper layers may not be final. The Standard Model, despite its success, is not a complete theory of everything. It does not include gravity in a fully consistent way, and it leaves several questions unanswered. Why do particles have the masses they do? Why are there exactly these types of particles and not others? What lies beyond this framework? These are open questions in modern physics, actively explored by research institutions such as CERN, where the Large Hadron Collider continues to probe matter at the highest energies we can currently achieve. In 2012, experiments at CERN confirmed the existence of the Higgs boson, a particle associated with the Higgs field. This field plays a crucial role in giving mass to other particles. Without it, atoms as we know them would not exist. The discovery was a major milestone, not because it introduced a completely new concept, but because it confirmed a missing piece of the Standard Model. And yet, even with this achievement, the sense remains that we are still uncovering layers, not reaching a final endpoint. So when we look at an atom now, we are not just seeing a small object. We are seeing a structure built from interactions between quarks, electrons, and force-carrying particles, all governed by underlying fields and principles. The atom becomes less like a solid object and more like a stable pattern, a temporary arrangement of deeper components. This idea can feel a little abstract at first, but it carries a quiet elegance. Reality at its core is not made of rigid pieces stacked together. It is made of relationships, interactions, rules that determine how components combine and behave, and those rules, though complex, are consistent across the universe. The same types of quarks that exist inside a proton in your body also exist inside the atoms of distant galaxies. The same forces that bind them together operate everywhere without exception. There is no special version of physics for one place, and a different version for another. It is all part of the same underlying system. So as we move deeper into the structure of matter, the picture becomes both simpler and more intricate at the same time. Simpler because everything reduces to a small set of fundamental ingredients. More intricate because the ways in which those ingredients interact give rise to endless variation. Atoms are no longer the final step. They are part of a layered structure, a hierarchy of organization, where each level builds upon the one beneath it, and somewhere within that structure, the familiar world begins to emerge. The textures, the colors, the sensations, all arising from these invisible components, quietly interacting in ways that, taken together, create the reality we experience every day. It is a reminder that even the most solid and familiar things are, at their core, composed of something far more subtle and far more dynamic than they first appear. As we continue to move deeper into the structure of matter, something begins to shift in a very fundamental way. The comfortable, familiar idea that objects have clear positions, well-defined paths, and predictable behavior starts to soften, and then, gradually, it dissolves. At the scale of atoms and the particles within them, the universe does not behave like a collection of tiny solid objects moving through empty space. Instead, it follows a set of rules that are subtle, probabilistic, and at times, quietly counterintuitive. This framework is known as quantum mechanics. Quantum mechanics is not just a refinement of earlier physics, it is a different way of describing reality itself. Rather than focusing on exact positions and motions, it describes systems in terms of probabilities, what is likely to happen rather than what must happen. One of the central ideas in quantum mechanics is the wave function, introduced by Erwin Schrödinger. The wave function is not a physical wave like water or sound. It is a mathematical description of all the possible states a particle can occupy. From this wave function, we can calculate probabilities, where an electron is most likely to be found, how it might move, how it interacts with other particles. But we cannot say, with certainty, exactly where it is at any given moment. This uncertainty is not due to a limitation in our instruments. It is not because we are not measuring carefully enough. It is built into the fabric of reality itself. Werner Heisenberg formalized this idea in what is known as the uncertainty principle. In simple terms, the more precisely you know a particle's position, the less precisely you can know its momentum, which is its motion. And the more precisely you know its momentum, the less precisely you can know its position. This is not a technical inconvenience, it is a fundamental limit. To express it clearly, the principle can be stated as the uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to a small constant value related to Planck's constant. That constant, known as Planck's constant, is incredibly small, roughly 6.6 times 10 to the minus 34 joule seconds, and yet it defines the scale at which quantum effects become important. At everyday scales, this uncertainty is so tiny that it is effectively invisible. A moving car, for example, has a position and speed that can be measured with extraordinary precision. But at the scale of electrons and atoms, this uncertainty becomes significant. It shapes how particles behave, how they interact, and how structures form. So instead of thinking of an electron as a tiny object orbiting a nucleus like a planet around a star, it is more accurate to think of it as a spread-out cloud of probability, a region where the electron might be found if we look for it, and even the act of looking, the act of measurement itself, plays a role in determining the outcome. This brings us to another subtle aspect of quantum mechanics. Observation is not passive. When we measure a quantum system, we are not simply revealing a pre-existing state. we are interacting with the system, influencing it in a way that affects the result. This is sometimes described as the collapse of the wave function, where a range of possibilities reduces to a single outcome. It is a strange idea, and one that has been debated for decades. Different interpretations of quantum mechanics attempt to explain what this really means. Some suggest that all possible outcomes exist simultaneously in a vast multiverse. Others propose that the act of measurement selects one outcome from many. What is important here is not which interpretation is correct, but the fact that at the quantum level, reality does not behave in a simple deterministic way. It is layered with possibility. Now, as quantum mechanics developed further, physicists began to notice something even more profound. Particles, the things we've been talking about as if they were small objects, may not be objects at all in the traditional sense. Instead, they can be understood as excitations of underlying fields. This idea forms the foundation of quantum field theory, developed through the work of scientists like Paul Dirac and later refined by Julian Schwinger, Richard Feynman, and others. In quantum field theory, the universe is filled with fields. These fields exist everywhere, at every point in space and time. There is an electron field, a quark field, a photon field, and so on. A particle is what happens when one of these fields is excited, when it vibrates in a particular way. It is similar, in a very loose sense, to a wave travelling across the surface of water. The wave is not a separate object from the water. It is a pattern, a movement, a temporary configuration of the underlying medium. In the same way, an electron is not a tiny bead moving through space. It is a localized excitation of the electron field. This perspective changes how we think about matter at the most fundamental level. Instead of a universe made of particles moving through empty space, we have a universe made of fields, with particles emerging as patterns within those fields. And this leads us to a particularly intriguing idea. What we often call empty space is not truly empty. Even in a perfect vacuum, where all particles have been removed, the underlying fields are still present. And because of the uncertainty principle, these fields cannot remain perfectly still. They fluctuate. These fluctuations give rise to what are known as vacuum fluctuations, temporary appearances of particle and antiparticle pairs that briefly come into existence before annihilating each other. This is not just theoretical speculation. The effects of vacuum fluctuations have been observed experimentally, for example in the Casimir effect, where two uncharged metal plates placed very close together experience a tiny force due to changes in the energy of the vacuum between them. So even in what appears to be empty space, there is activity, subtle, continuous, and unavoidable. It is a quiet reminder that the universe is never truly still. Now, bringing this back to atoms, we begin to see them in a new light. An atom is not just a collection of particles held together by forces. It is a stable configuration of interacting fields. The nucleus is formed from quark fields interacting through the strong force, mediated by gluons. The electrons are excitations of the electron field, existing in probability distributions shaped by the electromagnetic interaction. The structure of the atom, its energy levels, its stability, its ability to form bonds, all emerge from these underlying quantum rules, and those rules are consistent everywhere. The same quantum principles that govern an electron in a hydrogen atom also govern electrons in distant galaxies, billions of light years away. There is no variation, no local adjustment. The laws are the same. This universality is one of the most remarkable features of physics. It means that by studying atoms here in a laboratory on Earth, we're also learning about the behavior of matter across the entire universe. And perhaps more quietly, it suggests that the fabric of reality is deeply unified. At the surface level, the world appears diverse and complex, countless materials, forms, and structures. But beneath that diversity lies a common foundation: fields, probabilities, interactions. It is a little like listening to a vast symphony. At first, you hear the richness of the music, the different instruments, the shifting melodies. But if you listen more closely, you begin to notice the underlying patterns, the notes, the harmonies, the structure that holds everything together. Quantum mechanics and quantum field theory reveal that kind of structure in the physical world. They show us that what appears solid is, at a deeper level, dynamic. What appears certain is, in fact, probabilistic. What appears empty is quietly active. And all of this is happening constantly, everywhere, whether we notice it or not. So when we look at an atom now, we're not just seeing a small unit of matter. We are seeing a window into the fundamental nature of reality itself, a place where certainty gives way to possibility, where particles become patterns, and where the quiet activity of fields shapes everything that exists. It is not a chaotic picture. It is structured, consistent, and governed by precise laws. But it is also more subtle, more fluid, and more interconnected than our everyday intuition might suggest. And as we continue to explore these ideas, that subtlety begins to feel less like something strange and more like something quietly beautiful. Once atoms began to take shape as real, physical entities, something interesting started to happen. Scientists noticed patterns, not random patterns, not vague similarities, but consistent, repeating behaviors across different elements. Certain substances reacted in similar ways. Some formed comparable compounds. Others shared distinctive physical properties, like softness, reactivity, or the way they interacted with light. At first, these patterns appeared scattered, almost coincidental, but gradually, a deeper order began to reveal itself. In the mid-19th century, a Russian chemist named Dmitry Mendeleev took on the challenge of organizing the known elements. At that time, only around 60 elements had been identified, and their relationships were not fully understood. Mendeleev approached the problem with a mixture of careful observation and a kind of intuitive boldness. He arranged the elements by increasing atomic mass and began grouping them based on similar chemical properties. As he worked, something remarkable emerged. The properties of elements seemed to repeat at regular intervals. This repeating behavior became known as periodicity. But Mendeleev did something even more striking. Where the pattern appeared incomplete, he left gaps. Instead of forcing the known elements into a rigid structure, he allowed the pattern itself to guide him. He predicted that there must be undiscovered elements that would fit into those empty spaces, and he even estimated their properties in advance. And then, over time, those elements were discovered, with properties that closely matched his predictions. It was a powerful demonstration that the periodic table was not just a convenient arrangement. It was revealing something fundamental about the structure of matter. At this stage, however, the underlying reason for these patterns was not fully understood. Mendeleev had organized the elements based on observable behavior, but the deeper cause remained hidden. That insight came later, through the work of Henry Moseley in the early 20th century. Moseley studied the X-ray spectra emitted by different elements and discovered that each element could be uniquely identified by a number, the number of protons in its nucleus. This number became known as the atomic number. What Moseley showed was that the true ordering principle of the periodic table is not atomic mass, but atomic number. Each step across the table corresponds to an increase of 1 proton in the nucleus. This might seem like a small adjustment, but it clarified the entire structure. The atomic number determines the number of electrons in a neutral atom, and those electrons, arranged in specific energy levels, are responsible for the chemical behavior of the element. So the periodic table is not just a list of substances, it is a map of how electrons are arranged around nuclei, and how those arrangements lead to repeating patterns of behavior. To understand why these patterns repeat, we need to look back to quantum mechanics. Electrons in an atom do not occupy arbitrary positions. They exist in discrete energy levels, often referred to as shells or orbitals. Each level can hold a limited number of electrons, and these electrons arrange themselves according to specific rules, including the Pauli exclusion principle, which states that no 2 electrons can occupy the same quantum state within an atom. As you move from one element to the next, adding 1 proton and 1 electron at a time, these electrons fill the available energy levels in a structured way. When a new shell begins to fill, the chemical behavior changes, but as that shell fills up, patterns begin to repeat. This is why elements in the same column of the periodic table, known as groups, tend to have similar properties. They have similar electron configurations in their outermost shell, which is the region most involved in chemical interactions. For example, the elements in the first column, such as lithium, sodium, and potassium, each have 1 electron in their outermost shell. This makes them highly reactive, particularly with water. They tend to lose that single electron easily, forming positive ions. On the opposite side of the table, the noble gases such as helium, neon, and argon have completely filled outer shells. This makes them very stable and largely unreactive. They have little tendency to gain or lose electrons, so the periodic table becomes a reflection of underlying quantum structure, It shows how the arrangement of electrons, governed by quantum rules, leads to predictable patterns in chemical behavior. And those patterns are not limited to simple reactions. They extend to physical properties as well: the density of elements, their melting points, their electrical conductivity. All of these characteristics are influenced by atomic structure. As our understanding deepened, the periodic table itself continued to expand. In the 20th century, scientists began to create new elements artificially, extending the table beyond those found naturally on Earth. One of the key figures in this effort was Glenn T. Seaborg, an American chemist who played a central role in the discovery and characterization of transuranium elements with atomic numbers greater than uranium. Seaborg and his colleagues at institutions such as the University of California, Berkeley, used particle accelerators to create these elements by bombarding atomic nuclei with high-energy particles. This work not only added new entries to the periodic table, but also led to a reorganization of its structure. Seaborg proposed the actinide series, placing a group of heavy elements in a separate row beneath the main table, similar to the lanthanide series above it. This adjustment made the table more consistent and reflected the underlying electron configurations more accurately. It is worth noting that many of these heavy elements are highly unstable. Some exist for only fractions of a second before decaying into lighter elements, and yet, even these fleeting atoms follow the same fundamental rules. They fit into the periodic pattern, obey the same quantum principles, and contribute to our understanding of how matter behaves at its limits. So the periodic table becomes more than just a chart. It is a kind of map, a guide to the structure of matter. Each position in the table represents a specific arrangement of protons and electrons, and from that arrangement, a set of properties naturally follows. It is a system where small changes, adding a single proton, a single electron, can lead to noticeable differences in behavior, and yet those changes occur within a framework that is deeply ordered. This order reflects a deeper concept in physics known as symmetry. Symmetry in this context refers to patterns that remain consistent under certain transformations. The periodic table exhibits a form of symmetry in how properties repeat and how elements relate to one another. This symmetry is not perfect in a visual sense, but it emerges from the underlying quantum rules that govern electron behavior. It is a reminder that the complexity of the world is not random, it is structured, and that structure arises from simple, consistent principles applied over and over again. So when you look at the periodic table, you're not just looking at a list of elements, you're looking at a summary of how atoms are built, how electrons arrange themselves, and how those arrangements give rise to the chemical and physical properties of matter. It is a bridge between the abstract world of quantum mechanics and the tangible world of everyday experience. From the way metals conduct electricity, to the way oxygen supports life, to the way carbon forms the backbone of biological molecules, all of it can be traced back to patterns encoded in the periodic table, and perhaps most quietly it shows that even within the immense diversity of the universe, there is a kind of underlying order, a pattern that repeats, a structure that holds, a map that, once understood, allows us to navigate the building blocks of reality with a sense of clarity and even a little bit of calm. If atoms are the building blocks of everything, then there is another question quietly waiting beneath that idea. What holds those building blocks together? Why does an atom remain stable instead of simply falling apart? And what allows atoms to interact with one another, forming the vast range of materials we see around us? The answer lies in something less visible than atoms themselves, something that cannot be held or seen directly, but whose effects shape every structure in the universe: forces. In modern physics, there are four fundamental forces that govern all interactions in nature. They are the gravitational force, the electromagnetic force, the strong nuclear force, and the weak nuclear force. Each one operates across different scales, with different strengths and roles. Together, they form the underlying framework that allows matter to exist, organize, and evolve. Gravity is perhaps the most familiar. It is the force that pulls objects toward one another, giving weight to physical things and shaping the motion of planets, stars, and galaxies. It acts over vast distances, but at the scale of atoms, gravity is extremely weak. Its influence is almost negligible compared to the other forces. To put that into perspective, the electromagnetic force between two charged particles is many orders of magnitude stronger than the gravitational attraction between them. If gravity were the only force at play inside an atom, it would not be able to hold anything together. So while gravity dominates the large-scale structure of the universe, it plays only a minor role in the structure of atoms. The real work at the atomic level is carried out by the other three forces. The electromagnetic force is central to the structure of atoms and the interactions between them. It arises from electric charge. Protons carry a positive charge, electrons carry a negative charge, and these opposite charges attract one another. This attraction is what binds electrons to the nucleus, forming the structure of the atom. At the same time, like charges repel. Electrons repel other electrons, and protons repel other protons. This balance of attraction and repulsion creates a dynamic stability within the atom. It is not a rigid structure, but a carefully balanced system where forces are constantly at work. The electromagnetic force is also responsible for almost everything we experience in daily life. The sensation of touch, the rigidity of materials, the formation of chemical bonds, all of these arise from electromagnetic interactions between atoms. When you press your hand against a surface, it is not your atoms physically merging with the atoms of the surface. It is the electromagnetic force between electrons preventing them from occupying the same space, creating resistance. So even the feeling of solidity is, at its core, an interaction between electric charges. But there is another challenge inside the atom. The nucleus contains protons, all of which carry a positive charge. According to the electromagnetic force, they should repel each other strongly, and yet the nucleus remains intact. This is where the strong nuclear force comes into play. The strong force is the most powerful of the four fundamental forces, but it operates over a very short range, limited to distances on the scale of atomic nuclei. Its role is to bind protons and neutrons together, overcoming the electromagnetic repulsion between protons. Without the strong force, atomic nuclei would not exist. Matter as we know, it would not be possible. At an even deeper level, the strong force binds quarks together inside protons and neutrons, mediated by particles known as gluons. What makes the strong force particularly unusual is that it becomes stronger as the distance between quarks increases. This property, known as confinement, ensures that quarks remain bound together. It is a bit like trying to separate two objects connected by an elastic band that becomes tighter the more you stretch it. Eventually, instead of breaking the connection, the system rearranges itself, producing new bound combinations. So the strong force is not just a binding force, it is a stabilizing force that prevents matter from fragmenting into isolated components. The fourth fundamental force, the weak nuclear force, plays a more subtle but equally important role. The weak force is responsible for certain types of particle transformations, such as beta decay, where a neutron can transform into a proton, an electron, and a neutrino. This process is essential in nuclear physics and plays a key role in the behavior of radioactive elements, as well as in processes inside stars. While the weak force does not contribute directly to the structural stability of atoms in the same way as the strong and electromagnetic forces, it is crucial for understanding how matter changes over time. It allows particles to transform, enabling processes that would otherwise be impossible. As physicists studied these forces more deeply, they began to notice connections between them. In the 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg developed a theory that unified the electromagnetic force and the weak nuclear force into a single framework known as electroweak theory. According to this theory, at very high energies, such as those present in the early universe, the electromagnetic and weak forces are not separate. They are different aspects of a single, unified force. As the universe cooled, this symmetry was broken, and the forces began to behave differently. This idea of symmetry and symmetry breaking is central to modern physics. Symmetry in this context refers to the invariance of a system under certain transformations. A system is symmetric if it behaves the same way under those transformations. Gauge theories, which form the mathematical foundation of the Standard Model, are built on these symmetry principles. They describe how particles interact through forces by requiring that certain symmetries remain consistent. The electromagnetic force, for example, is described by a gauge theory based on the conservation of electric charge. The strong force and weak force are described by more complex symmetry groups, each with its own structure. While the mathematical details of gauge theory are intricate, the underlying idea is surprisingly simple. Forces arise from the requirement that certain properties of a system remain consistent across space and time. In other words, forces are not just added features of the universe, they are consequences of deeper principles. This perspective brings a kind of quiet elegance to the way we understand matter. Atoms are not held together by arbitrary mechanisms. They exist because the fundamental forces, governed by symmetry, create stable configurations of particles. The balance between attraction and repulsion, between binding and transformation, allows atoms to form, persist, and interact. And those interactions extend beyond individual atoms. The electromagnetic force, in particular, allows atoms to connect with one another, forming molecules and larger structures. It governs how electrons are shared or transferred between atoms, leading to chemical bonds. It shapes the way atoms arrange themselves in solids, liquids, and gases. It determines how energy is absorbed and emitted, how light interacts with matter, and how materials respond to their environment. So the forces that operate at the smallest scales also shape the world we experience. They are the hidden structure behind stability. Without them, atoms would not exist, molecules would not form, stars would not shine, life would not emerge. Everything depends on this delicate interplay of forces acting consistently across the universe. And perhaps most remarkably, these forces do not vary from place to place. The same electromagnetic interaction that binds electrons to a nucleus here also operates in distant galaxies. The same strong force that holds quarks together in a proton within your body also holds together the nuclei of atoms in the most remote regions of space. There is a universality to these laws, a consistency that allows complexity to arise without chaos. So when we think about atoms now, we begin to see them not just as collections of particles, but as systems stabilized by forces, structures that exist because of balance. And as those atoms begin to interact with one another, guided by these same forces, something new begins to emerge. Not just individual building blocks, but connections between them. And from those connections, the first steps toward chemistry, structure, and the rich diversity of matter begin to unfold. If atoms were only ever alone, drifting quietly without interacting, the universe would be a very simple place. There would be no water, no rocks, no air, no living systems. Just isolated building blocks never combining into anything larger. But atoms are not solitary. They are constantly interacting, influenced by the electromagnetic force, responding to the arrangement of electrons around them. And from these interactions emerges one of the most important processes in all of chemistry, the formation of chemical bonds. A chemical bond is not a physical hook or a rigid connection. It is not something you could point to and say, there it is. Instead, a bond is a stable arrangement of atoms that arises from the behavior of their electrons. At its core, bonding is about energy. Atoms tend to move toward configurations that are more stable, meaning lower in energy. When atoms come together in certain ways, their combined system can have less energy than when they are separate. That difference in energy is what holds them together. There are several main types of chemical bonds, each with its own characteristics, but all rooted in the same underlying principles. One of the simplest to understand is the ionic bond. In an ionic bond, one atom transfers one or more electrons to another atom. This transfer creates charged particles known as ions. One atom becomes positively charged, having lost electrons, and the other becomes negatively charged, having gained them. These opposite charges attract each other through the electromagnetic force, forming a bond. A classic example is sodium chloride, common table salt. A sodium atom tends to lose one electron, becoming a positively charged ion. A chlorine atom tends to gain that electron, becoming negatively charged. The attraction between these ions forms a stable structure, but this is not a single pair of atoms holding hands. In a solid crystal of sodium chloride, each ion is surrounded by many others in a repeating three-dimensional pattern, creating a lattice that extends throughout the material. This structure gives salt its characteristic properties, such as its crystalline form and its ability to dissolve in water. Another common type of bonding is the covalent bond. In this case, instead of transferring electrons, atoms share them. When two atoms come close together, their electron clouds overlap. The electrons are no longer associated with just one atom, but are shared between both. This shared arrangement lowers the energy of the system, creating a stable bond. Hydrogen gas provides a simple example. Two hydrogen atoms, each with one electron, come together and share their electrons, forming a molecule of two atoms held by a covalent bond. More complex molecules, such as water, involve multiple covalent bonds. In a water molecule, one oxygen atom shares electrons with two hydrogen atoms, forming a bent structure that gives water many of its unique properties. The concept of covalent bonding was developed and refined by scientists like Linus Pauling, who introduced the idea of electronegativity, a measure of how strongly an atom attracts electrons in a bond. Pauling's work helped explain why some bonds are purely covalent, while others have partial ionic character. In many cases, bonds exist along a spectrum rather than fitting neatly into one category. Then there is metallic bonding, which behaves quite differently. In a metal, atoms are arranged in a lattice, but their outer electrons are not confined to individual atoms or pairs of atoms. Instead, these electrons delocalized, meaning they move freely throughout the entire structure. This creates what is often described as a sea of electrons surrounding positively charged atomic cores. This freedom of movement allows metals to conduct electricity and heat efficiently. It also gives them properties like malleability, meaning they can be shaped without breaking, because the atoms can shift while maintaining their overall structure. So even though ionic, covalent and metallic bonds appear quite different, they all arise from the same underlying principle: the behavior of electrons in response to energy and electromagnetic interactions. As our understanding deepened, scientists began to move beyond simple models of bonds as fixed connections. They started to describe bonding in terms of quantum mechanics, where electrons are not particles following defined paths, but probability distributions shaped by wave functions. This led to the development of molecular orbital theory, associated with scientists such as Robert Mulliken and Friedrich Hund. In molecular orbital theory, when atoms come together, their atomic orbitals combine to form new orbitals that belong to the entire molecule, not just to individual atoms. Electrons occupy these molecular orbitals, which can extend over multiple atoms. Some of these orbitals lower the energy of the system and contribute to bonding, while others raise the energy and are known as antibonding orbitals. The stability of a molecule depends on how electrons fill these orbitals. This approach provides a more accurate and detailed description of bonding, especially for complex molecules where simple models fall short. It also reinforces an important idea. Bonds are not rigid connections. They are patterns of probability, regions where electrons are more likely to be found, creating stable arrangements of atoms. So when we say that two atoms are bonded, what we really mean is that their electron distributions have adjusted in a way that lowers the overall energy of the system. It is a subtle and dynamic process, not a fixed structure. This perspective also helps explain why bonds can break and reform. If energy is added to a system, for example through heat or light, electrons can be excited into higher energy states. This can weaken or break bonds, allowing atoms to separate or rearrange. Conversely, when atoms come together and form bonds, energy is often released, sometimes in the form of heat or light. This exchange of energy is at the heart of chemical reactions. But even at rest, bonds are not static. Atoms within a molecule are constantly vibrating, their positions shifting slightly as they respond to thermal energy. The bonds between them stretch and compress, never completely still. So the structures we think of as solid or fixed are, at the atomic level, gently in motion. Now, as atoms bond together, they form molecules. A molecule is simply a group of atoms held together by chemical bonds, but from this simple definition arises an incredible range of possibilities. 2 atoms can form a simple molecule like oxygen gas. 3 atoms can form water. Larger combinations can create complex organic molecules, including those essential for life. The number of possible arrangements grows rapidly as more atoms are involved, leading to a vast diversity of structures. And yet, all of this complexity arises from the same basic principles: electrons interacting, energy being minimized, and stable configurations forming. It is a bit like having a small set of rules for combining pieces and discovering that those rules can generate an almost endless variety of outcomes. So when atoms connect, they do not just form larger structures, they begin to create the foundation for chemistry itself. From simple bonds emerge molecules, from molecules emerge materials, and from those materials the structures of the natural world begin to take shape, all guided by the quiet, consistent behavior of electrons, moving through regions of probability, responding to forces, and settling into patterns that allow matter to hold together. and to evolve into something more. When atoms come together and form bonds, something new begins to appear, not just larger structures but shapes. A molecule is more than a collection of atoms. It is an arrangement, a geometry, a specific pattern in space that determines how that group of atoms behaves, interacts, and exists. In the simplest terms, a molecule is a group of atoms held together by chemical bonds. But that definition only tells part of the story. What truly matters is how those atoms are positioned relative to one another. Even with the same atoms, different arrangements can lead to entirely different properties. It is not just what a molecule is made of, but how it is shaped. This idea becomes clearer when we look at molecular geometry, a concept developed and refined through work by scientists such as Ronald Gillespie. Gillespie is known for the valence shell electron pair repulsion theory, often shortened to VSEPR. Despite the long name, the core idea is quite intuitive. Electrons repel each other. Because of this, electron pairs around a central atom arrange themselves as far apart as possible in three-dimensional space. This arrangement determines the overall shape of the molecule. For example, if a central atom is bonded to two other atoms and has no additional electron pairs, those atoms will arrange themselves in a straight line, forming a linear shape. If there are three bonded atoms, they tend to form a triangular arrangement, known as trigonal planar. With four bonds, the shape becomes tetrahedral, where the atoms are positioned at the corners of a three-dimensional pyramid. These shapes are not arbitrary. They arise directly from the behavior of electrons, which are guided by quantum mechanics and electromagnetic repulsion. And these shapes matter a great deal. Take water as an example. A water molecule consists of one oxygen atom bonded to two hydrogen atoms. If the atoms were arranged in a straight line, water would behave very differently. But because the oxygen atom has two additional pairs of electrons that are not involved in bonding, the molecule takes on a bent shape. The angle between the hydrogen atoms is a little over 100 degrees. This bent geometry creates an uneven distribution of charge, making water a polar molecule. One side is slightly negative, the other slightly positive. This polarity is what allows water molecules to attract each other, forming hydrogen bonds. It is the reason water has a relatively high boiling point, why it can dissolve so many substances, and why it plays such a central role in life. So a small difference in shape, just a slight bend, leads to a wide range of important properties. And this is a recurring theme in chemistry. Small changes at the atomic level can produce large differences at the macroscopic level. One of the most striking examples of this is chirality. Chirality refers to a property of asymmetry. A chiral molecule is one that cannot be superimposed onto its mirror image, much like your left and right hands. They are similar in structure, but not identical. This might seem like a subtle distinction, but in chemistry and biology, it can have profound consequences. Two molecules can have exactly the same atoms, connected in the same order, but differ only in their three-dimensional arrangement, and yet they can behave in completely different ways. In biological systems, many molecules are chiral, including amino acids and sugars. The specific orientation of these molecules determines how they interact with enzymes and other biological structures. In some cases, one version of a molecule can be beneficial, while its mirror image can be ineffective or even harmful. So here again, the arrangement of atoms, their spatial configuration, becomes critically important. It is not just the ingredients that matter, but the way they are assembled. This sensitivity to structure leads us to a broader concept known as emergence. Emergence describes how complex behavior and properties arise from simpler components. At the level of individual atoms, the rules are relatively straightforward. Electrons interact, energy is minimized, bonds form. But when atoms combine into molecules, new properties appear. A single oxygen atom behaves differently from a molecule of oxygen gas. A single carbon atom is not the same as a complex organic molecule. And as molecules grow larger and more intricate, their behavior becomes increasingly rich. These properties are not obvious from the individual atoms alone. They emerge from the interactions between them. It is a bit like music. A single note has a certain quality, but when multiple notes are combined in specific ways, melodies and harmonies appear. The resulting music is more than just the sum of its parts. In the same way, molecules exhibit behaviors that cannot be fully predicted by looking at individual atoms in isolation. And as molecules interact with each other, forming networks and structures, this emergence becomes even more pronounced. The texture of a material, the flexibility of a polymer, the biological activity of a protein. All of these depend on molecular structure. Even something as simple as smell is influenced by molecular shape. Certain molecules fit into receptors in the nose in specific ways, triggering signals that the brain interprets as different scents. So the world we experience, the way things feel, taste, and interact, is deeply connected to the shapes of molecules. And yet, beneath all of this complexity, the underlying rules remain consistent. Electrons repel, energy is minimized, stable configurations form. From these simple principles, an extraordinary range of structures emerges, and these structures are not static. Molecules are constantly in motion. They rotate, vibrate, and interact with their surroundings. Bonds stretch and compress. Shapes shift slightly as energy flows through the system. Temperature, pressure, and the presence of other molecules can all influence these dynamics. So even though we often think of molecules as fixed shapes, they are better understood as flexible dynamic systems. They are patterns that persist over time but never remain completely still. This constant motion becomes especially important when molecules begin to interact more actively, when they collide, rearrange, and transform. Because while structure defines what a molecule is, motion and interaction determine what it can become. And as these interactions increase in complexity, they begin to give rise to processes, changes over time, pathways through which matter can transform from one form into another. The quiet geometry of molecules sets the stage, but it is through their movement, their encounters, and their ability to rearrange that the next layer of complexity begins to unfold. As molecules form and settle into their shapes, there is a natural sense of stability. Bonds hold atoms together, structures persist and patterns repeat. But the universe is not a static place. Atoms and molecules are constantly in motion, gently vibrating, colliding, exchanging energy. And when the conditions are right, these interactions lead to something more dynamic, something that transforms matter itself. Chemical reactions. A chemical reaction is, at its most fundamental level, a rearrangement of atoms. The atoms themselves are not created or destroyed. Instead, the bonds between them are broken and new bonds are formed, leading to new combinations and new substances. This idea is captured in a principle known as the conservation of matter, first clearly articulated by Antoine Lavoisier. In any chemical reaction, the total amount of matter remains constant. The same atoms are present before and after the reaction, simply arranged differently. It is a bit like taking apart a structure made of building blocks and assembling it into a new form. The pieces remain the same, but the outcome can be entirely different. When hydrogen and oxygen combine to form water, the resulting molecule has properties that are very different from either gas alone. When carbon atoms rearrange, they can form soft graphite or hard diamond, depending on how they are bonded. So reactions are not just about change, they are about transformation. But what determines whether a reaction will occur? Why do some substances react readily, while others remain unchanged for long periods of time? To answer this, we need to consider energy. Every chemical system has an associated energy, and reactions tend to move towards states of lower energy. When a reaction releases energy, often in the form of heat or light, it is described as exothermic. When a reaction requires an input of energy, it is endothermic. However, energy alone does not tell the full story. A reaction might lead to a lower energy state, but still not occur unless certain conditions are met. This is because there is often an energy barrier that must be overcome for the reaction to proceed. This idea is central to reaction kinetics, the study of how fast reactions occur and the pathways they follow. In the early 20th century, Henry Eyring developed transition state theory, which describes how reactions pass through a high energy intermediate state before forming products. You can think of it as a kind of energy hill. Even if the final state is lower in energy, the system must first climb up this hill before it can descend. If the hill is too high, the reaction may occur very slowly, or not at all under normal conditions. This is why some reactions require heat, light, or a catalyst to proceed. A catalyst is a substance that lowers the energy barrier, allowing the reaction to occur more easily without being consumed in the process. Now, while kinetics describes how quickly reactions happen, thermodynamics describes whether they are favorable in the first place. Thermodynamics is the study of energy, heat, and the relationships between different forms of energy. One of its key concepts is entropy, a measure of disorder or the number of possible arrangements within a system. Ludwig Boltzmann provided a statistical interpretation of entropy, linking it to the number of microscopic configurations that correspond to a macroscopic state. In simple terms, a system tends to move towards states that can be realized in more ways, states that are more probable. This leads to one of the most important principles in physics and chemistry, the second law of thermodynamics. It can be expressed as, in any natural process, the total entropy of a closed system tends to increase over time. This does not mean that everything becomes chaotic or disordered in a visible sense. Rather, it means that systems evolve toward configurations that are statistically more likely. For example, if you drop a drop of ink into water, it spreads out over time. The molecules move from a more ordered arrangement to a more dispersed one, because there are far more ways for them to be spread out than to remain concentrated. This tendency toward increasing entropy gives direction to processes. It creates what is often referred to as the arrow of time. At the microscopic level, the laws of physics are mostly symmetric in time. They do not strongly distinguish between past and future. But at the macroscopic level, we observe a clear direction, from less probable states to more probable ones. This is why we see eggs breaking rather than spontaneously reassembling, and why heat flows from hot objects to cooler ones. Chemical reactions are influenced by both energy and entropy. A reaction is favorable if it leads to a state that is lower in energy, higher in entropy, or both. The balance between these factors determines whether a reaction will proceed. But there is another layer to consider. Not all systems are isolated or at equilibrium. In many cases, especially in natural environments, systems are open, exchanging energy and matter with their surroundings. These systems can exist far from equilibrium, where new kinds of behavior can emerge. The work of Ilya Prigogine explored these non-equilibrium systems, showing how order can arise in conditions where energy is flowing through a system. These are known as dissipative structures. A simple example is a convection pattern in a heated fluid, where organized motion emerges from what might otherwise seem like random movement. In chemical systems, non-equilibrium conditions can lead to oscillating reactions, pattern formation, and increased complexity. This is particularly important when considering the origins of life. Living systems are not in equilibrium. They maintain their structure by constantly exchanging energy and matter with their environment. They take in energy, use it to build and maintain complex structures, and release energy back into their surroundings. So while entropy tends to increase overall, local decreases in entropy can occur when energy is supplied. This allows for the emergence of organized, complex systems within a broader context of increasing entropy. Chemical reactions are the processes that make this possible. They allow atoms and molecules to rearrange, to explore different configurations, to form new structures and break old ones. Over time, these reactions can lead to increasingly complex arrangements, especially when guided by environmental conditions and energy flows. So when we think about chemical reactions, we are not just thinking about substances changing from one form to another. We are thinking about the mechanisms through which complexity arises. From simple rearrangements of atoms come the processes that shape materials, drive biological systems, and influence the evolution of the universe itself. And all of this unfolds within a framework defined by energy, probability, and time. A quiet, continuous process of transformation, where atoms, guided by fundamental principles, move from one configuration to another, gradually building the rich and dynamic world we experience. When we think about matter in everyday life, we often group it into familiar categories. Solids feel firm and hold their shape. Liquids flow and take the shape of their container. Gases expand to fill the space around them. These categories are useful, but they are only the beginning. At a deeper level, these states of matter are not defined by what something looks like or how it feels, but by how atoms and molecules behave collectively, how they move, how they interact, and how energy is distributed among them. A solid, for example, is a state where atoms or molecules are arranged in a fixed structure. They are not completely still, but they vibrate gently around stable positions. The forces between them are strong enough to hold them in place, giving solids their rigidity. In many solids, especially crystals, this arrangement follows a repeating pattern. Each atom occupies a specific position within a lattice, extending in all directions. This regular structure is what gives crystals their sharp edges and geometric shapes. A liquid, by contrast, has more freedom of movement. The atoms or molecules are still close together, but they are not locked into fixed positions. They can slide past one another, allowing the substance to flow. The forces between particles in a liquid are strong enough to keep them together, but not strong enough to maintain a rigid structure. This balance gives liquids their fluidity, while still allowing them to remain cohesive. A gas represents an even greater level of freedom. In a gas, particles are far apart and move rapidly in all directions. The forces between them are minimal, and their motion is largely independent. This is why gases expand to fill any available space and can be compressed relatively easily. So these three familiar states, solid, liquid, and gas, are really different expressions of the same underlying components, shaped by temperature, pressure, and the strength of interactions between particles. As energy increases, particles move more vigorously, and the structure of matter becomes less constrained. As energy decreases, motion slows, and structure becomes more ordered. But these are not the only possible states. Under certain conditions, matter behaves in ways that go far beyond these everyday categories. One such state is plasma. Plasma forms when a gas is heated to such high temperatures that electrons are stripped away from atoms, creating a mixture of positively charged ions and free electrons. This state is often described as an ionized gas, but it behaves quite differently from an ordinary gas. Because it consists of charged particles, plasma responds strongly to electric and magnetic fields. Plasma is actually the most common state of matter in the visible universe. Stars, including our Sun, are composed of plasma. Lightning, auroras, and even the faint glow of certain types of lamps are examples of plasma on Earth. In plasma, the behavior of matter is dominated not just by individual particle motion, but by collective interactions involving large numbers of charged particles moving together. At the opposite extreme, where temperatures are brought extremely close to absolute zero, another unusual state appears: the Bose-Einstein condensate. This state was first predicted by Satyendra Nath Bose and Albert Einstein in the early 20th century, but it was not experimentally realized until the late 1990s. In a Bose-Einstein condensate, a group of atoms is cooled to such low temperatures that their individual quantum states begin to overlap. Instead of behaving as separate particles, they act as a single quantum entity. It is as though many atoms lose their individuality and move together in perfect synchrony. This leads to remarkable properties. The condensate can exhibit coherence across a macroscopic scale, meaning that quantum effects become visible at sizes much larger than a single atom. It is a reminder that the boundaries between particles and waves, between individuality and collective behavior, are not always as clear as they seem. Closely related to this is the phenomenon of superfluidity, studied extensively by Piotr Kapitsa. In a superfluid, certain liquids, such as helium at very low temperatures, can flow without viscosity. This means they experience no resistance to motion. They can climb the walls of a container, flow through tiny openings, and continue moving indefinitely without losing energy. These behaviors are not intuitive, but they arise naturally from the quantum properties of the system when particles move in a highly coordinated way. So as we explore these different states of matter, a pattern begins to emerge. Matter is not defined solely by what it is made of, but by how its components behave together. The same atoms can exist in very different states depending on their energy and environment. Water can be a solid, a liquid, or a gas, depending on temperature and pressure. Under more extreme conditions, other states become possible. This idea leads us to think of matter not as a fixed category, but as a spectrum of behaviors. At one end, particles are tightly bound and highly ordered. At the other, they are free and energetic. In between, there are countless variations, each with its own characteristics. And throughout all of this, the underlying rules remain the same. Atoms interact through forces, energy influences motion, structures emerge from the balance between these factors. But what becomes especially important is the idea of collective behavior. When large numbers of atoms or molecules interact, their combined behavior can differ significantly from that of individual particles. A single atom does not have a temperature in the usual sense, but a large collection of atoms can exhibit temperature as a measure of their average energy. A single molecule does not flow, but a collection of molecules can form a liquid with viscosity and surface tension. These properties are not present in the individual components, They emerge from the interactions between many particles. So matter, as we experience it, is not just about atoms. It is about systems of atoms, behaving together, responding to conditions, and forming patterns that can be stable, dynamic, or somewhere in between. And these patterns are not limited to the environments we encounter on Earth. Across the universe, matter exists under conditions far more extreme than those we experience here. In the cores of stars, temperatures reach millions of degrees, and matter exists as dense plasma undergoing nuclear reactions. In the vast emptiness between stars, atoms and molecules drift through cold, diffuse clouds, forming the raw material for future stars and planets. On the surfaces of neutron stars, matter is compressed to densities so high that atomic structure itself begins to break down. So the states of matter we observe on Earth are just a small part of a much larger picture, a spectrum of possibilities shaped by temperature, pressure, and the fundamental forces that govern atomic interactions. And as we begin to consider these broader environments, the role of atoms expands even further. They are not just the building blocks of familiar materials. They are participants in a much larger cosmic story, one where matter changes state, evolves under extreme conditions, and takes on new forms as it moves through different regions of the universe. From the quiet solidity of a stone, to the flowing motion of a liquid, to the glowing plasma of a star, all of it emerges from the same underlying components, behaving collectively in response to their surroundings. A continuous expression of how atoms together create the many forms of matter we observe. If atoms are the building blocks of everything, then there is a deeper and rather poetic question waiting beneath that idea. Where did those atoms come from? The hydrogen in the water you drink, the carbon in your body, the oxygen you breathe, these atoms were not always here. They were formed long ago in environments far more extreme than anything we encounter on Earth. To understand their origin, we need to look to the stars. Stars are not just points of light in the sky. They are vast, self-contained systems where matter is transformed under intense pressure and temperature. Deep within their cores, a process known as nuclear fusion takes place. Nuclear fusion is different from chemical reactions. In chemistry, atoms rearrange their electrons and form new bonds, but the nuclei remain unchanged. In nuclear fusion, the nuclei themselves combine, forming new elements. At the core of a typical star, such as our Sun, temperatures reach around 15 million degrees, and pressures are immense. Under these conditions, hydrogen nuclei, which are simply protons, move so rapidly that they can overcome their natural electromagnetic repulsion. When two protons come close enough, the strong nuclear force takes over, binding them together. Through a series of steps, these protons ultimately fuse to form helium. This process releases a tremendous amount of energy. The energy produced by nuclear fusion is what powers stars, allowing them to shine for millions or billions of years. It is also the source of nearly all the energy that reaches Earth, driving weather, supporting life, and sustaining ecosystems. But fusion does not stop with helium. In more massive stars where the core temperature and pressure are even higher, helium nuclei can combine to form heavier elements. This is where things become especially interesting. The formation of carbon, one of the most important elements for life, occurs through a process known as the triple alpha process. In this process, 3 helium nuclei, each containing 2 protons and 2 neutrons, combine to form a carbon nucleus. However, this process is not straightforward. When 2 helium nuclei come together, they form a short-lived intermediate called beryllium-8. This intermediate is highly unstable and tends to break apart almost immediately. For carbon to form, a 3rd helium nucleus must collide with this unstable beryllium nucleus before it decays. The probability of this happening is quite low under ordinary conditions, and yet, carbon exists in abundance throughout the universe. The key to this puzzle lies in a concept known as resonance. Fred Hoyle, a British astrophysicist, proposed that there must be a specific energy level within the carbon nucleus that enhances the likelihood of this reaction. This resonance would allow the 3 helium nuclei to combine more efficiently under stellar conditions. Hoyle's prediction was later confirmed experimentally, providing a crucial piece of evidence for our understanding of stellar nucleosynthesis. It is a subtle and remarkable detail. Without this resonance, the formation of carbon in stars would be far less efficient, and the chemical composition of the universe would be very different. And since carbon is essential for life as we know it, This small detail has profound implications. The broader framework for understanding how elements are formed in stars was developed through the work of Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, often referred to as the B2FH team. In a landmark paper published in 1957, they outlined the processes by which elements are synthesized in stars, a field known as stellar nucleosynthesis. Their work described how lighter elements are fused into heavier ones through a series of nuclear reactions, depending on the mass and stage of evolution of the star. In smaller stars, fusion may stop at helium or carbon. In larger stars, the process continues, forming elements such as oxygen, neon, silicon, and eventually iron. Iron represents a kind of endpoint for fusion in stars. Fusing iron does not release energy in the same way as lighter elements. Instead, it requires energy, making it an unfavorable process under normal stellar conditions. As a result, once a star builds up a core rich in iron, it can no longer sustain fusion in the same way. This leads to dramatic consequences. In massive stars, the build-up of an iron core can trigger a catastrophic collapse, followed by a powerful explosion known as a supernova. But even before considering such explosive events, it is already clear that stars act as atomic factories. They take the simplest element, hydrogen, and through a series of nuclear processes, create a wide range of heavier elements. These elements are then distributed into space through stellar winds or, in more dramatic cases, through supernova explosions. Over time, this enriched material becomes part of new stars, planets, and eventually living systems. So the atoms that make up your body were not created in isolation. They are part of a long, continuous process of cosmic evolution. Hydrogen formed shortly after the Big Bang. Heavier elements were forged in the cores of stars. Those elements were scattered into space, incorporated into new structures, and eventually became part of the environment in which life could emerge. This process unfolds over billions of years. It is not fast, and it is not directed in any intentional way. It is simply the natural outcome of physical laws operating consistently across the universe. And yet, from this process arises the rich diversity of elements that make chemistry possible. Carbon, oxygen, nitrogen, iron, each with its own properties, each capable of forming different types of bonds, each contributing to the structures we observe. So when we think about atoms now, we can begin to see them not just as building blocks, but as products of a much larger story. They carry with them a kind of history, a record of the processes that formed them. The iron in your blood, for example, was likely formed in the core of a massive star that lived and died long before our solar system existed. The calcium in your bones may have been part of a stellar environment where temperatures and pressures were far beyond anything we can easily imagine. Even the oxygen you breathe was once part of a nuclear reaction deep within a star. There is something quietly humbling in that realization. The atoms that make up your body are not unique or newly created. They are ancient, recycled, and shared across the universe. And this brings us to a broader perspective. Stars are not just sources of light and heat, they are engines of transformation. They take simple building blocks and, through processes governed by fundamental forces in nuclear physics, create the elements that enable complexity. Without stars, the universe would be composed mostly of hydrogen and helium, with little variation and limited potential for forming complex structures. With stars, the universe becomes chemically rich. It gains the diversity needed for planets, for materials, for life. So the story of atoms is not confined to the microscopic scale. It extends outward into the vast structures of the cosmos. From the quiet interactions of particles within a nucleus to the immense processes occurring in the cores of stars, there is a continuous thread, a connection between the smallest scales and the largest. And as we follow that thread, we begin to see how the formation of atoms is not just a detail of physics, but a central part of the story of the universe itself, a story in which matter evolves, transforms, and gradually builds the conditions for everything that comes after. As stars quietly build elements in their cores, there is a natural limit to what they can create through steady fusion. Once iron forms, the process that has sustained the star for millions or billions of years begins to falter, and when that balance breaks, the result is not a gentle transition. It is an explosion. A supernova is one of the most powerful events in the universe. In a brief moment, a single star can release more energy than our sun will emit over its entire lifetime. For a short time, it can outshine an entire galaxy. But beyond the spectacle, supernovae serve a deeper purpose. They create and distribute some of the heaviest elements in existence. When a massive star reaches the end of its life, its core collapses under gravity. The outer layers then rebound outward in a violent explosion. During this collapse and explosion, conditions become extreme, temperatures reaching billions of degrees and pressures rising to extraordinary levels. In these conditions, atomic nuclei are bombarded by vast numbers of neutrons. This leads to a process known as rapid neutron capture, or the R process. In the R process, atomic nuclei capture neutrons so quickly that they do not have time to decay between captures. As more and more neutrons are added, the nucleus becomes heavier and increasingly unstable. Eventually, these neutron-rich nuclei undergo a series of transformations, converting neutrons into protons through the weak nuclear force. This process changes the identity of the element, producing heavier elements further along the periodic table. Through this mechanism, elements heavier than iron are formed, including gold, platinum, uranium, and many others. So the gold in a ring, the uranium in certain rocks, the rare elements used in advanced technologies, all of them owe their existence to these brief, intense moments in the life of a star. Supernovae do not just create these elements, they scatter them. The explosion sends material outward at speeds of thousands of kilometers per second, dispersing newly formed elements into the surrounding space. Over time, this material mixes with interstellar gas and dust, enriching it with a wider range of atomic building blocks. This enriched material becomes the foundation for future stars and planetary systems. But supernovae are not the only environments where heavy elements are formed. In recent years, another process has come into focus, one that involves some of the most extreme objects in the universe: neutron stars. A neutron star is the collapsed core of a massive star, left behind after a supernova. It is an object of incredible density. A teaspoon of neutron star material would weigh billions of tons on Earth. These stars are composed almost entirely of neutrons, packed together so tightly that atomic structure as we know it no longer exists in the same form. When two neutron stars orbit each other and eventually collide, the result is an event known as a neutron star merger. These mergers are among the most energetic and violent events in the universe. They produce intense bursts of radiation, gravitational waves, and conditions ideal for rapid neutron capture. In fact, neutron star mergers are now understood to be one of the primary sources of the heaviest elements. In 2017, a collaboration of observatories, including the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves from such a merger. This event, labelled GW170817, was also observed across the electromagnetic spectrum. The combined observations provided strong evidence that heavy elements, including gold and platinum, were formed during the merger. It was a remarkable confirmation of theoretical predictions, linking the behaviour of extreme astrophysical objects to the composition of matter here on Earth. The discovery also highlighted the importance of gravitational waves, ripples in space-time predicted by Albert Einstein's general theory of relativity. These waves carry information about massive cosmic events, allowing scientists to study phenomena that would otherwise be difficult to observe. The connection between neutron stars and pulsars was first identified by Jocelyn Bell Burnell in 1967, when she detected regular radio pulses from a previously unknown type of object. These pulses were later understood to be rapidly rotating neutron stars, emitting beams of radiation like cosmic lighthouses. Her discovery opened a new window into the study of extreme matter and the behaviour of stars after their explosive end. So across the universe, in both supernovae and neutron star mergers, there are environments where matter is pushed to its limits. Temperatures, densities, and energies reach levels that allow atomic nuclei to be transformed in ways that are not possible under ordinary conditions. And from these extreme processes, the periodic table is extended. Elements that cannot be formed in the steady cores of stars are created in these brief, intense events, and then, just as quickly, they are released. This dispersal is essential. If heavy elements remained locked inside stars or confined to isolated regions, they would not contribute to the formation of planets or life. But the violence of these events ensures that the elements are spread widely. Over time, the material ejected from supernovae and neutron star mergers becomes part of the interstellar medium, a vast diffuse mixture of gas and dust that fills the space between stars. This medium is not empty. It contains atoms, molecules, and small solid particles, all enriched by previous generations of stars. Gradually, under the influence of gravity, regions of this material begin to collapse, forming new stars and planetary systems. So the elements created in one generation of stars become the raw material for the next. This process is often described as cosmic recycling. Atoms are not confined to a single object or location. They move, mix, and are reused over immense timescales. A carbon atom formed in one star might later become part of a molecule in a cloud, then part of a planet, and eventually part of a living organism. The same is true for heavier elements. The gold in a piece of jewellery may have originated in a neutron star merger billions of years ago. The iron in your blood may have been formed in the core of a star that exploded long before the sun was born. These atoms have travelled vast distances, undergone multiple transformations, and become part of entirely new structures. So when we look at matter now, we can begin to see it as part of a continuous cycle: formation, transformation, dispersal, and recombination. Each stage governed by the same fundamental laws, each contributing to the evolving complexity of the universe. And while the processes themselves can be dramatic, involving explosions, collisions, and extreme conditions, the outcome is something more gradual and enduring. A steady enrichment of the universe with the elements needed to build planets, materials, and life. From the quiet fusion in stellar cores to the explosive creation of heavy elements, atoms are constantly being reshaped and redistributed, not lost, not destroyed, but rearranged and carried forward. A continuous journey through space and time, linking the life cycles of stars to the matter that eventually becomes part of worlds, and perhaps part of you. After the immense energy of stellar explosions and the quiet intensity of neutron star mergers, the universe does not rush forward. Instead, it settles, gradually redistributing what has been created. The heavy elements forged in those brief powerful events are not lost to space. They become part of something far more gentle yet just as important. They enter the interstellar medium. The interstellar medium is the vast expanse of gas and dust that exists between stars within a galaxy. At first glance, it might seem like empty space, but it is anything but empty. It contains atoms, ions, molecules, and tiny solid particles known as cosmic dust. The density of this medium is extremely low by everyday standards. In some regions, there may be only a few atoms per cubic centimetre. For comparison, the air around you contains on the order of 10 to the power of 19 molecules in the same volume, and yet across the enormous scales of galaxies, this sparse material becomes significant. Within the interstellar medium, there are regions where matter is slightly denser. Over time, gravity begins to act on these regions, drawing material inward. As atoms and molecules gather, they form structures known as molecular clouds. Molecular clouds are cold, dense regions of space where atoms combine to form molecules, particularly molecular hydrogen. Temperatures in these clouds can drop to just a few tens of degrees above absolute zero. Despite their cold and diffuse nature, these clouds can be immense, spanning dozens or even hundreds of light years. Within them, the building blocks of future stars and planetary systems quietly accumulate. It is here, in these dark and often obscured regions, that the cycle of matter begins again. Atoms that were once part of stars, that were scattered through supernova explosions or ejected from stellar winds, now drift together in these clouds. They are no longer part of a single star, but part of a shared reservoir of material. Given enough time, small fluctuations in density within a molecular cloud can grow. Gravity pulls more material into these regions, increasing their mass and density. As the cloud contracts, its core begins to heat up. Eventually, conditions become intense enough to ignite nuclear fusion, and a new star is born. So the atoms that once belonged to older stars become part of new ones. This is the essence of cosmic recycling. Matter is not static. It moves through different stages, different environments, different structures. An atom might begin as hydrogen formed in the early universe. It may become part of a star, where it is fused into a heavier element. It might then be ejected into space, travel through the interstellar medium, and eventually become part of a new star or a planet. Over billions of years, atoms can pass through multiple generations of stars. They are reused, reshaped, and redistributed. This continuous cycle links the life and death of stars to the broader evolution of galaxies, and it is not just a random process. The structure of galaxies plays a role in how this recycling occurs. Galaxies are not uniform. They have regions of higher and lower density, spiral arms where star formation is more active, and vast halos of dark matter that influence their overall dynamics. The work of Vera Rubin in the 20th century revealed something unexpected about galaxies. By studying the rotation of galaxies, she found that stars at the outer edges were moving much faster than predicted by the visible mass alone. This led to the conclusion that galaxies contain large amounts of unseen mass, now referred to as dark matter. While dark matter does not interact with atoms in the same way as ordinary matter, its gravitational influence shapes the structure of galaxies. It affects how gas and dust move, how molecular clouds form, and how stars are distributed. So even though dark matter is invisible, it plays a role in the environments where atomic recycling takes place. Within this larger structure, the interstellar medium becomes a kind of connective tissue. It links stars across time and space, allowing material to move between different stages of cosmic evolution. And within this medium, chemistry begins to emerge in subtle ways. Even in the cold depths of molecular clouds, simple molecules form. Hydrogen atoms combine into molecular hydrogen. Carbon and oxygen can form carbon monoxide. More complex organic molecules have also been detected, including methanol and formaldehyde. These molecules form on the surfaces of dust grains, or through reactions in the gas phase, often driven by cosmic radiation. So even before stars and planets form, the ingredients for more complex chemistry are already present. And this brings us to a particularly striking realization. The atoms that make up living systems, including those in your own body, have traveled through this cosmic cycle. The carbon in your cells was once part of a star. The oxygen you breathe may have been formed in a stellar core and later released into space. The nitrogen in your DNA likely followed a similar path. These atoms have been part of other structures, other systems, long before becoming part of you. They have existed for billions of years, moving through different environments, undergoing transformations, and participating in the ongoing evolution of the universe. There is something quietly profound in that. It means that life is not separate from the cosmos. It is part of the same process. The same atoms that form distant stars also form the molecules that make up living organisms. The same physical laws that govern galaxies also govern the chemistry within a single cell. It is all connected. And this connection is not abstract. It is physical, tangible, and continuous. So when we think about atoms now, we can see them not just as building blocks, but as travelers. They move through time and space, carried by the processes of stellar evolution, gravitational collapse, and chemical interaction. They are part of a cycle that spans billions of years and vast distances. And as this cycle continues, the material within molecular clouds begins to take on new forms. Regions within these clouds collapse further, forming disks of gas and dust around young stars. Within these disks, particles begin to collide, stick together, and grow, from small grains to larger aggregates, from aggregates to planetesimals, and eventually to planets. So the story of atoms, which began with simple particles and then moved through stars and explosions, now begins to focus on something more familiar. Worlds, solid surfaces, atmospheres, oceans, environments where atoms combine in increasingly complex ways, and all of it begins with a quiet gathering of material in the interstellar medium, a slow, steady process of accumulation that sets the stage for the formation of planets and the next chapter in the journey of matter. As clouds of gas and dust gather around young stars, something begins to take shape, slowly, quietly, and over immense spans of time. Within these rotating disks, tiny particles collide. At first, these are microscopic grains, fragments of minerals and frozen compounds drifting through space. When they meet, they sometimes stick together, held by electrostatic forces or simple physical contact. Over time, these small clusters grow. They become larger aggregates, then pebble-sized objects, then kilometre-scale bodies known as planetesimals. Gravity begins to play a more significant role, pulling these bodies together, guiding their motion, and encouraging further growth. Through countless collisions and gradual accumulation, some of these planetesimals grow into protoplanets, the early forms of planets. This process is known as planetary formation. It is not a smooth or orderly progression. Collisions can be violent, reshaping growing bodies, melting material, and redistributing elements. Some objects merge, others break apart, and some are ejected entirely from the system. And yet, through this dynamic process, stable planetary systems begin to emerge. Once a planet reaches a certain size, another process begins to take hold: differentiation. Differentiation refers to the separation of materials within a planet based on their density. In the early stages of planetary formation, especially when collisions generate significant heat, parts of a young planet may become partially or fully molten. In this molten state, heavier elements such as iron and nickel tend to sink toward the center, forming a dense core. Lighter materials, including silicates, rise toward the surface, forming a mantle and eventually a crust. This layered structure is a defining feature of many planets, including Earth. At the center lies a metallic core surrounded by a thick mantle of rock and topped by a relatively thin crust where we live. This structure is not just a passive arrangement. It influences the behavior of the planet in important ways. The movement of material within the mantle drives processes such as plate tectonics. The presence of a liquid outer core can generate a magnetic field, which protects the planet from charged particles emitted by its star. So the internal arrangement of atoms within a planet shapes its long-term evolution. Understanding this structure has been the work of many scientists, including Claire Patterson, whose research provided one of the most accurate estimates of the age of the Earth. In the 1950s, Patterson used uranium-lead dating on meteorites to determine that the Earth is approximately 4.5 billion years old. His work also led to important discoveries about the distribution of lead in the environment, highlighting the impact of human activity on natural systems. Through geochemical studies like these, scientists have been able to trace the history of planetary materials, understanding how atoms have moved, combined, and separated over time. At the surface of a planet, atoms and molecules form minerals, solid substances with specific chemical compositions and crystal structures. A mineral is defined not just by what it is made of, but by how its atoms are arranged. In a crystal, atoms are organized in a repeating, orderly pattern that extends in all directions. This arrangement determines the physical properties of the mineral, including its hardness, density, and the way it interacts with light. For example, both graphite and diamond are made entirely of carbon atoms. In graphite, the atoms are arranged in flat layers, with weak forces between them. This allows the layers to slide over one another, making graphite soft and useful for writing. In diamond, the same carbon atoms are arranged in a three-dimensional network of strong covalent bonds. This structure makes diamond one of the hardest known natural materials. So once again, we see that the arrangement of atoms, their geometry and bonding, determines the properties of matter. Across a planet, different minerals combine to form rocks, and different rocks form landscapes. Mountains, valleys, deserts, and ocean basins all arise from the behavior of atoms arranged in specific ways, responding to forces such as gravity, heat, and pressure. Even the atmosphere of a planet is shaped by atomic interactions. Gases such as nitrogen, oxygen, and carbon dioxide interact with sunlight, with each other, and with the surface. These interactions influence temperature, weather patterns, and the overall climate. On Earth, the presence of liquid water plays a central role. Water interacts with rocks, dissolving minerals, transporting material, and shaping the surface over time. So a planet is not just a collection of atoms, it is a dynamic system where atoms are constantly moving, interacting, and reorganizing. The same fundamental principles we have been exploring, atomic structure, bonding, energy, and forces, are now expressed on a planetary scale. And yet, even within this complexity, the underlying simplicity remains. Atoms combine according to consistent rules. Structures emerge from those combinations. Processes unfold over time, guided by energy and interaction. From the smallest particles to entire worlds, the same patterns repeat. What becomes especially interesting is how certain environments on planets allow for increasingly complex chemistry. On a planet with the right conditions, suitable temperature, the presence of liquid water, a stable energy source, atoms can combine into more intricate molecules. Carbon, in particular, plays a unique role here. Because of its ability to form four stable bonds, carbon can create a vast array of molecular structures, from simple chains to complex three-dimensional frameworks. These carbon-based molecules can interact in ways that lead to new behaviors, new properties, new possibilities. On Earth, this chemistry eventually gave rise to life. But even before that point, the stage had to be set. Atoms had to be assembled into planets. Planets had to develop stable environments. Chemical processes had to unfold over time, gradually increasing in complexity. So the formation of worlds is not just about rocks and gases. It is about creating the conditions where atoms can explore new configurations, where molecules can become more complex, where the quiet interactions of matter can begin to take on new significance. From the cooling of molten surfaces to the formation of oceans and atmospheres, each step builds upon the last, and within these environments something begins to emerge, not suddenly and not in a single moment, but gradually, through countless interactions. A new level of organization, one that still depends entirely on atoms, but uses them in ways that are more intricate, more dynamic, and more responsive than anything we have seen so far. And it is here, within the structure of worlds shaped by atomic interactions, that the next transformation begins to take form. As atoms gather on the surface of a planet and begin to interact in increasingly complex ways, there comes a point where chemistry takes on a new character. The same principles are still at work: electrons interacting, energy being exchanged, molecules forming and breaking apart. But now those processes begin to organize into systems that are not just stable, but active. This is where chemistry begins to blur into biology. At the center of this transition is a particular element that appears again and again in living systems: carbon. Carbon has a unique ability to form 4 stable covalent bonds, allowing it to connect with other atoms in a wide variety of ways. It can form long chains, branching structures, and complex rings. It can bond with hydrogen, oxygen, nitrogen, and other elements, creating a vast range of possible molecules. This flexibility makes carbon the foundation of organic chemistry, the chemistry of life. From carbon arise biomolecules, the molecular structures that make life possible. There are 4 major classes of biomolecules: carbohydrates, which serve as sources of energy and structural components; lipids, which form cell membranes and store energy; proteins, which perform a wide range of functions, from catalyzing chemical reactions to providing structural support; and nucleic acids, which store and transmit genetic information. Each of these molecules is built from atoms arranged in specific ways, forming structures that are both stable and dynamic. Proteins, for example, are made from chains of amino acids. These chains fold into intricate 3-dimensional shapes, and the function of a protein depends critically on its shape. A slight change in the arrangement of atoms can alter the shape of the protein, and therefore its function. So once again, the theme returns. Structure determines behavior. But now, the structures are becoming more complex and the behaviors more varied. One of the most profound developments in this progression is the emergence of information. In living systems, molecules do not just interact randomly, they carry instructions. This idea was explored by Erwin Schrödinger in his book What is Life, published in 1944. Schrödinger proposed that living systems must contain a kind of a periodic crystal, a structure capable of storing complex information in a stable form. This idea anticipated the discovery of deoxyribonucleic acid, or DNA. DNA is a molecule composed of 2 strands that wind around each other in a double helix structure. Each strand is made up of a sequence of smaller units called nucleotides, which include the bases adenine, thymine, cytosine, and guanine. The sequence of these bases encodes information. This information determines how proteins are built, how cells function, and how organisms develop. The structure of DNA was famously described by James Watson and Francis Crick in 1953, building on crucial experimental data from Rosalind Franklin, whose X-ray diffraction images revealed the helical structure of the molecule. What makes DNA remarkable is not just its structure, but its ability to replicate. When a cell divides, the DNA strands separate, and each strand serves as a template for the formation of a new complementary strand. This process allows genetic information to be passed from one generation to the next. So atoms arranged into molecules are now forming systems that can store, copy, and transmit information. This is a significant step. It means that the behavior of the system is not determined solely by immediate interactions, but also by encoded instructions, and these instructions can change over time. Through processes such as mutation and natural selection, the sequences in DNA can evolve, leading to new structures and functions. This introduces a new kind of complexity, not just structural complexity, but informational complexity. Manfred Eigen, a German physicist and chemist, studied how molecular systems can self-organize and evolve. He introduced the concept of the hypercycle, a model describing how molecules can form networks that support each other's replication. These ideas help bridge the gap between simple chemistry and the more complex behavior associated with living systems. They suggest that life does not emerge from a single sudden event, but from a gradual increase in organization and interaction. From simple molecules to networks of molecules, from networks to systems capable of maintaining and reproducing themselves. So life can be understood as a form of structured atomic complexity. It is not separate from the laws of physics and chemistry. It arises from them. Every process in a living organism, from the beating of a heart to the firing of a neuron, is ultimately based on the interactions of atoms and molecules. Cells are composed of membranes, proteins, nucleic acids, and other molecules, all interacting in highly coordinated ways. These interactions are governed by the same principles we have been exploring: bonding, energy, probability, and forces. But the organization of these components allows for behaviors that are not seen in simpler systems. Metabolism, for example, involves a network of chemical reactions that convert energy and materials into forms that the organism can use. Homeostasis involves maintaining stable internal conditions despite changes in the environment. Reproduction allows the system to create copies of itself, passing on its structure and information. These are not properties of individual atoms. They are properties of systems built from atoms. So the transition from chemistry to biology is not a change in the fundamental rules. It is a change in the level of organization. Atoms form molecules. Molecules form networks. Networks form systems that can sustain themselves, respond to their environment, and evolve over time. And throughout this process, the same underlying components remain: carbon, hydrogen, oxygen, nitrogen, arranged in different ways, forming different structures, participating in different interactions. There is no new type of matter introduced, only new patterns. And this brings us to a quiet but powerful realization. Life, in all its complexity, is built from the same atoms that make up the rest of the universe. There is no special substance that separates living matter from non-living matter. The difference lies in how the atoms are arranged, how they interact, and how those interactions are organized. It is a difference of structure, not substance. So when we look at a living organism, we are not seeing something separate from the physical world. We are seeing a highly organized expression of it, a system where atoms have come together in ways that allow for complexity, adaptability, and continuity. And this system, like everything else, is subject to the same fundamental laws. It exists because those laws allow for stable, complex arrangements. It evolves because those arrangements can change over time, and it persists because energy flows through it, maintaining its structure against the tendency toward disorder. So the story of atoms now extends into something deeply familiar. From the formation of stars to the creation of elements, from the assembly of planets to the emergence of molecules, and now to the organization of life. A continuous progression, where each step builds upon the last, guided by consistent principles. And at every stage, the same quiet foundation remains: atoms, interacting, combining, and forming the structures that make everything possible. As we step back and take in the full picture, something quietly remarkable begins to come into focus. From the smallest particles to the largest structures, the same underlying rules are at work. The same atoms, governed by the same forces, following the same principles of energy and interaction. And yet, from those simple ingredients, an immense diversity of forms has emerged. This brings us to an idea that sits at the heart of modern science: emergence. Emergence describes how complex systems and behaviors arise from simpler components interacting according to consistent rules. It is not that new laws suddenly appear at higher levels. Instead, new patterns form, patterns that are not obvious when looking only at the individual parts. A single atom does not exhibit life, thought, or consciousness. But when atoms combine into molecules, and molecules into networks, and those networks into highly organized systems, entirely new properties can appear. These properties are not contained within any single component. They arise from the relationships between them. This idea has been explored in fields such as complexity science. where researchers study how systems with many interacting parts can give rise to organized behavior. Stuart Kauffman, for example, examined how networks of chemical reactions can spontaneously organize into self-sustaining systems. His work suggests that under the right conditions, complexity is not an accident. It is a natural outcome of interacting components. In such systems, order does not need to be imposed from the outside. It can emerge from within. This is known as self-organization. Self-organization occurs when a system develops structure or pattern without a central controller. It can be seen in many contexts, from the formation of snowflakes, to the patterns of convection in fluids, to the coordinated behavior of cells in a living organism. In each case, local interactions between components lead to global patterns. Atoms follow simple rules. But when many atoms interact, those rules can produce structures that are intricate, dynamic, and surprisingly robust. And this raises an interesting question. If the underlying rules are so simple, why does the world appear so complex? Part of the answer lies in the number of interactions. Even a small system of molecules can have an enormous number of possible configurations. As the number of components increases, the number of possible arrangements grows rapidly. This creates a rich landscape of possibilities, where certain patterns become stable and persist over time. But there is another factor to consider: the transition between different levels of description. At the quantum level, as we've seen, particles behave in terms of probabilities. Their positions and properties are not fixed, but described by wave functions and uncertainty. And yet, at the scale of everyday experience, objects appear stable, well-defined, and predictable. A chair does not exist in a cloud of probability. It sits where it is, solid and reliable. So how does this transition occur? One of the key concepts here is decoherence, developed in part through the work of Wojciech Zurek. Decoherence describes how quantum systems interacting with their environment lose their coherent quantum behavior. The delicate superpositions that exist at the quantum level become effectively averaged out as the system interacts with many surrounding particles. In simple terms, the environment continuously measures the system, causing it to behave in a more classical way. This process does not eliminate quantum mechanics, but it explains why quantum effects are not usually visible at larger scales. It provides a bridge between the probabilistic world of atoms and the more deterministic world of everyday objects. So the solidity of a table, the stability of a planet, the reliability of physical structures, all of these emerge from underlying quantum processes that have been shaped by interactions with the environment. This layered structure of reality leads to an ongoing discussion in philosophy and science. The relationship between reductionism and holism. Reductionism is the idea that complex systems can be understood entirely by breaking them down into their smallest parts and studying those parts in isolation. Holism, on the other hand, emphasizes that the behavior of a system as a whole cannot always be fully explained by its individual components. Alfred North Whitehead, a philosopher and mathematician, argued for a process-based view of reality, where relationships and interactions are as fundamental as the objects themselves. From this perspective, it is not enough to understand atoms individually. One must also understand how they relate to each other, how they form patterns, and how those patterns evolve over time. In practice, both perspectives are valuable. Reductionism allows us to identify the basic building blocks and the laws that govern them. Holism reminds us that new properties can emerge at higher levels of organization. Together, they provide a more complete picture. Atoms obey consistent rules, but the structures they form can exhibit behaviors that are not immediately apparent from those rules alone. This is not a contradiction. It is a reflection of how complexity arises. So when we look at the world now, we can begin to see it in layers. At the deepest level, there are fundamental particles and fields. From these arise atoms structured by forces and quantum mechanics. Atoms combine to form molecules, which take on specific shapes and properties. Molecules interact to form materials, liquids, gases, and more complex systems. From these systems emerge biological processes, ecosystems, and eventually conscious beings capable of reflecting on their own existence. And at every level, the same foundational elements are present. The same atoms, the same interactions, the same physical laws. There is no sudden break where one set of rules ends and another begins. Instead, there is continuity, a gradual unfolding of complexity from simplicity. This continuity brings with it a sense of unity. The atoms in your body are not fundamentally different from the atoms in a distant star. The processes that govern chemical reactions in a cell are based on the same principles that govern interactions in interstellar space. Everything is connected through the same underlying framework, and perhaps there is something quietly reassuring in that idea. That despite the vast scale of the universe, despite the diversity of forms and structures, there is a common foundation, a shared set of rules that gives rise to everything. So the story of atoms is not just about the smallest components of matter, it is about how those components, through interaction and organization, give rise to the entire structure of reality, from simplicity to complexity, from particles to patterns, from atoms to everything.